Example on compatible system. Show that the system or the equations p square plus q square is equal to 1, and another equation is p square plus q square x minus pz is equal to 0 are compatible, and find one parameter family of common solution. That is, if these two are compatible, then they have a common solution, and we have to find the common solution of these two equations. Okay, so we know that when the system or equations are compatible, suppose this is the equation number 1 and this is equation number 2, that is p square plus q square minus 1 is equal to 0 as the equation number 1, and p square plus q square x minus pz is equal to 0 equation number 2, and denoted by small f and small g. This equation number 1 is f and this is g. Or this, after simplification, we have p square x plus q square x minus pz is equal to 0. This is a equation number 2. And now we know that when the equations are compatible, if dava f by dava g, if dava fg dava pq, the Jacobian is not equal to 0. And if this is equal to 0, that is this quantity, this dava fg dava xp plus p dava fg dava zp plus dava fg dava yq plus q dava fg dava zq is equal to 0. This is equal to 0. This equation is satisfied. Then we say the equations are compatible. There are two conditions. So this dava fg dava pq, this Jacobian is not equal to 0. On that domain, this function is compatible and this equal to 0. That is the second condition. Actually, this is the first condition, and the second condition is actually f and g are that is the equation is integrable. So what is the definition of compatible equation, compatible system? So this is the definition of compatible system. The Jacobian dava fg dava pq is not equal to 0 on that domain, and this equation dz is equal to p dx plus q dy is integrable. What is p and q? P and q are the functions of x, y, z, and obtained by solving equation number 1 and 2. After solving equation 1 and 2, we have p and q, and substitute that p and q. And if this equation is integral, and in this theorem, we know that this equation dz is equal to p dx plus q dy is integrable if this is equal to 0. Now, in order to check whether this dz is equal to p dx plus q dy is integrable, what we have to show? This equation is satisfied. This is equal to 0. So these two conditions are satisfied, then we say the function is that the equations, the solutions are compatible. So first we will show that the Jacobian dava fg dava pq is not equal to 0, and then equation is 0. So see this example, we have to show first these two solutions or two equations f and g are compatible. This is the equation. So f is the equation number 1, g as the equation number 2, and we have to show, we have to find first dava fg dava pq is what? This Jacobian is dava f dava p dava f by dava q dava g by dava p dava g by dava q, this determinant. And this dava f by dava p is 2p with respect to derivative. Dava f by dava q is 2q, and its determinant dava g dava p dava g dava p, that is the derivative with respect to p is 2px minus z with respect to p, and with dava g by dava q means with respect to q is 2qx, determinant complete. And then solve this determinant, this into this 2pqx minus this into this 2p minus 2pqx minus 2qz, okay, in bracket, but in bracket this into this minus this into this minus this into this. And then it is after simplification we have this, and 4pqx minus 4pqx get cancelled, minus minus become plus 2zq or 2qz, and this is not equal to 0 for all xy. This is not depend on x, and so this function is this Jacobian is not equal to 0 over every domain d, okay, for all xy. Then we have to verify this is equal to 0. So what is it? The dava f by dava fg dava xp plus p dava fg dava zp plus dava fg dava yq plus q dava fg dava zq is equal to 0. Now we will find all these four Jacobians. Dava fg dava xp is dava f by dava x, dava f by dava p, dava g by dava x, dava g by dava p, and then is equal to dava f by dava x with respect to x derivative is 0, and dava f by dava p is 2p. Then dava g by dava x is p square plus q square with respect to x, then p square plus q square, and then dava g by dava p is 2px minus z, and then this into this is 0 minus 2p in bracket p square plus q square, that is we have minus 2p cube minus 2pq square. Then dava f by dava fg dava zp is equal to dava f by dava z, dava f by dava p, dava g by dava z, dava g by dava p. And then dava f by dava z, if you observe this, is there is no z, so its derivative is 0, dava f by dava z is 0. And then dava f by dava p is 2p, dava g by dava z is minus p. Then dava g by dava p is 2px minus z. And then this into this is 0, and this into this is minus become plus 2p square. So 2p square is the answer. Then dava f by dava fg dava yq. Dava fg dava yq is dava f by dava y, dava f by dava q, dava g by dava y, dava g by dava q is equal to dava f by dava y is 0 because y there is no y in g. So dava f by dava y is 0. Then dava f by dava p is 2p. Dava g by dava a z, dava g by dava z is minus p. Dava g by dava z is minus p. And dava g by dava q is q is 2qx. And then its determinant, this into this is 0 minus in bracket minus 2pq, that is plus 2pq is the answer. Then consider LHS of this equation. Dava f by dava fg dava xp plus p dava fg dava zp plus dava fg dava yq plus q dava fg dava zq. Consider LHS is equal to, substitute the values. Dava fg dava xp, this Jacobian is this minus 2pq minus 2pq square plus p into dava fg dava zp is 2p square plus dava fg dava yq is 0 and plus q into this 2pq plus 2pq, and then multiplication is simplification is minus 2pq square plus 2pq plus 2pq square, and addition of all these four property quantity is 0, and therefore the given equations are compatible, or the given solutions are compatible. So that satisfies these two property, that is this Jacobian is not equal to 0 and this equation is satisfied. If this is equal to 0, we have 0 answer here. Therefore the given equations or the given solutions are compatible. Now we have to find the one parameter family of common solutions. So we know that, what is your note, how we can find one parameter family of common solution. So here is the note after one parameter family of common solution can be obtained by solving equation dz is equal to p dx plus q dy. So now we will find p and q by solving 1 and 2. We will obtain p and q, and then we have to find dz is equal to, we have to solve the equation dz is equal to p dx plus q dy. So first we will find the values of p and q by solving given equation number 1 and 2. So these are the equation number 1 and 2. Now we have to find the values of p and q. So p square plus q square is 1 from equation number 1. We have p square plus q square is 1. Put in equation number 2. What we have? The equation 2 is this, p square plus q square is 1. So x minus pz is equal to 0. We have x minus pz is equal to 0, and x minus pz is equal to 0 means x is equal to pz and p is equal to x by z. and this put this value p is equal to x by z in equation number 1. What is the equation number 1? P square plus q square is 1. So p square is x square by z square plus q square is equal to 1. So q square is 1 minus x square by z square. Take a z square as LCM. So z square minus x square, and therefore q is equal to, this is the value of q square. So take the root of both sides. So q is equal to root x z square minus x square divided by root of z square is z. So we know that one parameter family of common solution can be obtained by solving the equation dz is equal to p dx plus q dy. That is dz is equal to, substitute p as x by z dx plus q as root z square minus x square by z dy, and then dividing, multiplying throughout by z, we have z dz is equal to x dx plus root z square minus x square dy, and this dz is equal to p dx plus q dy is the Papian differential equation. And we know that how we can obtain the solution of Papian differential equation. There are different methods, and by inspection we can obtain the solution of the Papian differential equation. If it is a one variable separable or applied Nathalie's method or a homogeneous Papian differential equation, there are different types. The general type is what? By adjust the derivatives terms, we can obtain the solution by integrating both sides. So after integration, so we have to ready this factor, these all these factors for integration. So multiplying by z, so all these, this equation dz is equal to p dx plus dy q dy is a Papian differential equation. So apply one of the method of the Papian differential equation to obtain the solution of this equation dz is equal to p dx plus q dy. So here multiply throughout by z, and then we have this, and then z dz minus x dx is equal to root z square minus x square dy. Then dividing this, shift this z square minus x square to numerator, to LHS, we have z dz minus x dx divided by root z square minus x square is equal to dy. Now this is one variable separable now, and then this is the derivative of root z square minus x square. This is the derivative of root z square minus. So what is the derivative of root z square minus x square? 1 by 2 times root z square minus x square, that is root x. What is the derivative of root x? 1 by 2 times root x is 1 by root z square minus x square into derivative of z square minus x square is 2z dz minus 2x dx, the derivative of z square minus x square. And then take 2 as common, cancel the 2, we have z dz minus x dx divided by root z square minus x square. That is, this is the derivative of root z square minus x square dy. Integrating both sides, derivative and integration get cancelled, so we have root z square minus x square is equal to dy, integration is y, plus constant of integration c. So remain this equation as a last equation, or squaring both sides. So what do we have? Z square minus x square is equal to y plus c bracket square. Either write this as the final answer or this as the final answer, and this is one parameter family of common solution. This is one parameter family of common solution. So this is the problem on the compatible system. We also solve one more problem. So this is the problem that show that the equation f is equal to xp minus yq minus x is equal to 0, and g is equal to x square p plus q minus xz is equal to 0 are compatible, and find one parameter family of common solution. So denote the given two equation by one by f and another by g. Xp minus yq minus x is equal to 0, and x square p minus plus q minus xz is equal to 0 as equation number 2. Now we will find dabba fg dabba pq, determinant Jacobian dabba fp dabba pq is dabba f by dabba p dabba f by dabba q, and dabba g by dabba p dabba g by dabba q. All right, this, and then it is we have x x square. Either write dabba f by dabba p, then dabba f by dabba f by dabba q, and the determinant dabba g dabba p dabba g dabba q. We have the same answer both, in both way. We have the same answer. Either this, write this as a value of this Jacobian, or dabba f by dabba f by dabba p dabba f by dabba q, and the second row is dabba g by dabba p dabba g by dabba q. In both methods we have the same answer, this answer. So dabba f by dabba p is x, dabba g by dabba p is x square, then dabba f by dabba q is minus y, and dabba g by dabba q is 1, and then its determinant is x minus plus x square y. So take x as common, 1 plus xy is not equal to 0. Denote this is not equal to 0 on the domain D that does not contains the points xy such that x is 0 or 1 plus xy is 0. So when this is 0, x into x1, 1 plus xy, when this quantity is 0, either if x is 0 or 1 plus xy is equal to 0. So except that, so this function, this dabba g dabba pq, the Jacobian is not equal to 0. When is not equal to 0? If x is not equal to 0 and not or, and 1 plus xy both are not equal to 0. So this is not equal to 0 on the domain does not contain the points xy such that either x is 0 or 1 plus xy 0. So does not contain. So means this is the except the points where either x is 0 or 1 plus xy 0, except these points where x is 0 or 1 plus xy is 0. Other than these points, D is the domain on which the function is compatible, or this is not equal to 0. So no need to write this directly, write this is not equal to 0. If write either this sentence or write comma if x is not equal to 0 and 1 plus xy is not equal to 0. Okay, so accept that point. Then we have to verify dabba fg dabba xp plus p dabba fg dabba zp plus dabba fg dabba yq plus q, not here phi and psi or p and q, q in the place of psi we write q, and in place of phi we write p, because phi, p means phi and q means psi. Dabba fg dabba zq is equal to 0. We have to verify this. Now we will find dabba fg dabba xp. First, dabba fg dabba xp is dabba f by dabba p, dabba f by dabba f dabba f by dabba x, dabba f by dabba p. And second row is dabba g by dabba x, dabba g by dabba p. Or write this. And we have the same answer in both methods. That is write this Jacobian as dabba f by dabba x, dabba f by dabba p, as the first row, and second row as dabba g by dabba x, dabba g by dabba p. Or write this. Then we have the same answer. Dabba f by dabba x, dabba f by dabba x is what? Dabba f by dabba x is p. Then p minus 1, dabba f by dabba x. This is p and this is 0, minus x derivative is minus 1. And dabba g by dabba x, dabba g by dabba x is twice xp minus z, twice xp minus z. And dabba f by dabba p, dabba f by dabba p is x, and dabba g by dabba p is x square. Dabba g by dabba p is x square. And solve this determinant. This into this minus this into this, we have this answer, xz minus x square in bracket p plus 1. All right, this as the last answer. Then the second determinant, dabba fg, second quantity Jacobian, dabba fg dabba zp is what? Again, dabba f by dabba z, dabba f by dabba p, dabba g by dabba z, dabba g by dabba p. Okay, and then dabba f by dabba z is 0 because there is no z in f. And dabba f by dabba p, dabba f by dabba p is what? Is x, dabba g by dabba z is minus x, dabba g by dabba p is x square. And then answer is this into this is 0, minus minus plus x square. Then next determinant, dabba fg dabba yq, dabba fg dabba yq, this quantity. So dabba fg dabba yq is what? Dabba f by dabba y, dabba f by dabba q, dabba g by dabba y, dabba g by dabba q. Then dabba f by dabba y is with respect to y derivative. Observe this, with respect to y derivative is minus q. Then dabba f by dabba with respect to dabba f by dabba q, dabba f by dabba q is minus y. Similarly, the dabba g by dabba y is 0 because there is no y in g. So dabba g by dabba y is 0, and dabba g by dabba q is 1. And so its simplification is this into this minus q minus 0. That is minus q is the answer. and then dabba f by dabba g, dabba f g dabba z q is dabba f by dabba z, dabba f by dabba q, dabba g by dabba z, dabba z, dabba g by dabba q, and we have dabba f by dabba z is 0 because there is no z. Dabba f by dabba q is minus y in this way. Dabba g by dabba z is minus x. This is 1, and so this 0 minus minus x and minus y becomes plus x into y. So 0 minus xy, that is minus xy is the answer. So consider the LHS of that equation and substitute the values of this quantity xz minus p, right? This phi as p. Dabba f by dabba fg dabba zp, dabba fg dabba zp is x square. So p x square or x square p plus dabba dabba fg dabba yq is minus q minus q minus q, the values, plus psi means q x into y. Okay, this quantity minus xqy. Don't write this step. Don't write this step. This step. This value is minus x square. Then this value is what? P into x square. P into x square. Yes, this value. Dabba fg dabba xp dabba fg dabba zp. This value is what? P in bracket. P in bracket. P in bracket this value xz minus x square p plus 1. So we have the value x square p yes dabba fg dabba xp is xz minus x square p minus x square. Okay, the value of this quantity is first three quantity plus p dabba f by dabba fg dabba zp is x square, so minus p x square plus p x square minus this value is q minus q, and this value is what? Q psi means q minus xyq, and then this get cancelled, and so we have minus x square plus hz minus q minus xyq. Now we have to show this is equal to 0. So use second equation. So value of, from equation number 2, value of xz, so this xz to RHS. So xz is x square p plus q. So substitute this xz as x square p plus q minus xyq as it is, and then minus q plus q get cancelled. So we have minus x square plus x square p plus q plus q minus q becomes 0 minus xy q by 2. Okay, and then this step is I can repeat it here, and then minus x square plus x square p, this minus p and plus p get cancelled, and minus xyq by equation number 1, xyq, value of xyq. So xyq. So shift this value to RHS, it's become yq and multiply by x. So x square p minus x square is the value of xyq. X square p minus x square. X square p minus x square. So minus minus become plus because this is minus sign. So minus x square p plus x square from equation number 1. And therefore we have the answer 0 minus x square plus x square p. Okay, we have the answer 0. The value of xyq is what? Value of xyq from equation number 1. Value of xyq is xp square minus x square. So write in bracket x square p minus x square in bracket and after negative effect of negative sign we have minus x square p plus x square, and the value is 0. So the given equations are compatible. So this equation is satisfied, and therefore the given equations are compatible. Equation 1 and 2 are compatible. Now we will find the values of p and q from equation number 1 and 2. So multiplying equation 2 by q and adding 1 and 2 we give this equation number 1, and multiply equation number 2 by equation number this 2 by q, and we have this uh, x square yp plus yq multiplying by q to equation second. So we have x square yp plus yq minus xy z is equal to 0. Equation 1 and 2. Multiplying equation 2 by q and then add, we have this minus xyz x square yp, that is multiplying equation 2 by y, don't write q here, y, multiplying equation 2 by y and adding 1 and 2. So this is 1, and after multiplying equation 2 by y we have this. So addition of these two is minus yq and plus yq get cancelled. So we have to find the values of p and q. So in order to find the value of 1 and from equation 1 and 2 with the values of p and q, we have to cancel either q or p. So multiplying equation 2 by y, don't write here q, write y, and adding, we have this get cancelled, xp plus x square yp minus x minus xyz is equal to 0. Take x common and take xp as common. So we have, and then shift to RHS, we have this, and so x get cancelled. So p is 1 plus yz divided by 1 plus xy, and substitute this value of p in equation number 1. This is equation 1, xp minus yq minus x is equal to 0. So xp, p is 1 plus yz divided by 1 plus xy minus yq minus x is equal to 0. So we have this y, shift this minus yq to RHS, and then take divide by y to throughout equation. So x by y, here we have x by y, here is q, and then q is, take x by y as common, 1 plus yz divided by 1 plus xy minus 1, and then LCM is 1 plus xy, 1 plus yz minus 1 plus xy, 1 plus yz minus 1 minus xy divided by 1 plus xy. So we have 1 and minus 1 get cancelled, yz minus xy divided by 1 plus xy. This is the value of q. Take this y as common and take cancel this y. So xz minus x divided by 1 plus xy is the value of xy. Now consider the equation dz is equal to pdx plus q dy. In order to find one parameter family of common solution, we have to solve this equation. dz is equal to pdx plus q dy. So consider the equation dz is equal to p dx plus q dy, and substitute p as 1 plus yz divided by 1 plus xy dx, q as z in bracket x z minus x divided by 1 plus xy dy. Then here some adjustment, add xy and subtract xy, 1 plus xy minus xy plus yz divided by this, and then 1 plus xy divided by 1 plus xy is 1 plus yz minus xy divided by 1 plus xy dx, this quantity as it is x, and then it is dx plus yz minus xy 1 plus xy dx, xz minus x 1 plus xy dy. This is our all for the adjustment in order to integrate this equation. dz is equal to p dx plus q dy. So this is the adjustment. Add plus xy, subtract plus xy, subtract and add xy, and then we have, and then shift this dx to LHS. So dz minus dx is the LHS now, this quantity as it is, and take 1 plus xy as LCM. So we have y, take y common, z minus x dx plus x z minus x dy, and then take z minus x as common and shift to LHS. Take this z minus x common from these two and shift to LHS. So we have dz minus dx divided by z minus x is equal to y dx plus x divided by 1 plus xy, and then integrating, and this is the integration of log, this is the derivative of log z minus x, or integration of this is what, f dash x divided by fx rule. Integration of f dash x divided by fx is log fx, log z minus x. And again, the derivative of 1 plus xy is what, derivative of 1 is 0, and derivative of x into y is x dy plus y dx. Derivative of x into y is what, this x dy plus y dx. And this is again by using rule, f dash x divided by fx is log 1 plus xy, plus log c is the constant. And so this is as the final answer, or we shift this log 1 plus xy to LHS. So we have log z minus x divided by log divided by 1 plus xy, z minus x divided by 1 plus xy, cancel log of both sides. So we have the answer, z minus x divided by 1 plus xy is equal to constant. So write that two more steps, z by x, shift this log 1 plus xy to LHS. So we have log z minus x divided by 1 plus xy is equal to log c, log cancel log of both sides. We have final answer, z minus x divided by 1 plus xy is equal to c, and this is the one parameter family of common solution. Okay, so these are the two solved problems. So these are the problems for exercise. So show that the following equations are compatible, or following solutions are compatible, and if they are compatible, then find one parameter family of common solution. If they are not compatible, then don't find the one parameter family of common solution. So this is about the topic compatible solutions. In the next lecture, we will start the Charpit's method.